Hello, and welcome to Astronomy 100. In this video, we're going to continue our discussion of the concept of brightness versus luminosity. In the previous video, remember that luminosity is the amount of energy that a star produces and puts off into space, and the brightness is the appearance of that energy at some distance away. And we introduced the term apparent magnitude last time, which is the appearance of the brightness of an object as seen by an observer on the Earth, and we attached a numbering system to this appearance of brightness. Remember that the numbering system appears to be backwards when you first look at it. The idea is some objects are bright, some objects are faint, and the numbering system goes from a small number representing bright objects to a larger number representing faint objects. So it is kind of intuitively backwards, and just make sure you get used to that notion. What I'm going to do in this video is show you some examples. So let's start with the first example. If we were to look in the sky and find the constellation of Scorpius, these are the stars that make up that constellation of Scorpius. Scorpius means scorpion. The head of the scorpion is here, the body of the scorpion, and then of course the curving tail with the stinger on the end. Now, this is a good example of apparent magnitude because some of the stars in Scorpius have particular numbers that are easily able to be used as examples. The star right here is the star called Antares, and it's a good example of a first magnitude star. Now notice that this star right here, which is a second magnitude star, is fainter. So the bigger the number, the fainter the star. But if you remember in the previous video, the numbering system is one that is exponential, meaning any one single magnitude step difference is actually a difference in brightness of 2.5. So a second magnitude star is 2.5 times fainter than a first magnitude star. And then when we go to a third magnitude star, it is yet another 2.5 times fainter. And then a fourth magnitude star is yet again 2.5 times fainter. So any 5 magnitude steps is a difference in brightness of 100 times. Any 1 magnitude step is a difference in brightness of 2.5. So remember, it's not just simply getting a little bit fainter and a little bit fainter still, it is dropping off quite dramatically. 2.5 times fainter, 2.5 times fainter still, and so forth. Now what I want to show you is a scale of brightness change. This kind of helps reinforce the idea, and it also allows me to show you the difference between some of the brightest objects in the sky versus some of the faintest. So this is called the apparent magnitude scale. We go from bottom to top, we go from fainter to brighter, but remember the numbering system is backwards. So when the numbers are very big, it's faint, and when the numbers get smaller, we're actually getting brighter. Remember that we have to include 0, and that allows us to get into negative numbers. The original system from Hipparchus was to judge the brightest stars to the faintest stars in the sky, and his numbering system went from 1 to 6. Magnitude 1 was the brightest stars, magnitude 6 were the faintest. But let's now include some other objects for reference. For instance, I mentioned in the previous video how the sun is the brightest thing that you could see in the sky. That's natural. And of course, it's because the sun is very close to us. On this magnitude scale, the sun has an apparent magnitude of negative 26.5. So notice, it's very, very deep into the negative numbers because the sun is very, very bright as we see it in the sky. The next brightest thing that you would see that's natural would be the full moon. When the moon is full, it's very bright, and it has a magnitude of negative 12.6. In fact, it's bright enough you could read by a full moon. It's a very bright object. Venus, at its brightest, is negative 4.7. Now notice I qualify the statement by saying Venus at its brightest. Think for a moment why Venus would have to be judged as different brightnesses at different times. The idea is, if you remember, Venus demonstrates phases. We see phases as Venus is going around the sun. That's something that Galileo discovered. And so Venus can change its brightness because of its phase as well as how close or how far from the Earth it is. At its brightest, it's negative 4.7. Now, when we go beyond the limit of what you can see with your eye, we would of course have to use a pair of binoculars or perhaps a telescope. And notice that a typical pair of binoculars will get you to a magnitude of about +10. So in other words, you can see quite a bit fainter than what your eye can see by using a pair of binoculars. And notice that Pluto gets you down to about +15. So Pluto is very faint. It is much fainter than what binoculars would allow you to see. Now here's what I want you to notice. So notice that a pair of binoculars allow you to see a magnitude of +10, and Pluto is +15. You might think that this difference of 5 magnitudes means that Pluto is only 5 times fainter than what binoculars allow you to do. But remember, every 5 steps is a difference of 100 times. So in reality, Pluto is 100 times fainter than what a pair of binoculars would allow you to see in the sky. Remember, it's an exponential change. The largest telescopes in the world get us down to about +25, which is extraordinarily faint, even though the number is very, very big. So the magnitude scale is a backwards way of thinking of it, but it's an important way to make sure you understand that the smaller the number, or the more negative the number, the brighter, and the larger the number, or the more positive the number is, the fainter. It is backwards, but it is what we're stuck with. It's something that's been in place for thousands of years, and there's just no desire to change that. So we just have to get used to it. Now, the other idea that I want to introduce today is related to the luminosity of the star. Remember that luminosity is how much energy that the star is actually producing. So let me show you the concept of how we measure the luminosity of a star. It is kind of a strange idea, but let me start with this picture here. What if we had a universe where every single star in the universe were exactly the same distance away from the sun? So there is no difference in the distance to any one of these stars. They're exactly the same distance away from the sun. And let's make it a distance of 33 light years. So if every star in the universe were 33 light years away, then the distance to the star has now nothing to do with the appearance of its brightness, because they're all the same distance away. Now here's what I want you to notice. Some of the stars appear bright, some of the stars appear faint. If they're all exactly the same distance away, the ones that appear bright have to be stars that produce more energy, and the ones that appear faint have to be stars that produce less energy, because the appearance of their brightness has nothing to do with their distance. This is the concept called absolute magnitude, and we abbreviate it with a capital M, but absolute magnitude has kind of a strange definition. Let me show it to you in words. Absolute magnitude is the apparent magnitude of a star if its distance were 33 light years. So it is a little bit tough to imagine what this is trying to say, and I do understand for a basic astronomy class this is something that is a fairly complicated idea. So whether you can truly understand that definition or not isn't as important as the idea that absolute magnitude is related to the amount of energy that the star is emitting. So what is really more important of these two statements is that you understand the second one, that the absolute magnitude of a star is related to the amount of energy that the star is producing, or its luminosity. So in reality, absolute magnitude is an indicator of the star's luminosity, and apparent magnitude is an indicator of the star's brightness. And if you can understand that that's the connection between the two, then these terms, of course, will be something that we can use. So you can go outside and look at the brightness of a star, but you don't know how much energy the star is producing because you don't know how far away it is, or you can measure something else about the star that will tell you the amount of energy that the star is producing, and that's the idea of absolute magnitude. And we're going to use these terms and bring them in and kind of relate them to each other. Now, speaking of the idea of the luminosity of a star, let me show you the example of the luminosity of our star, the sun. Now, the sun's energy is something that we can measure. It is because we know the distance to the sun. And if you know the distance to the sun, and if you go outside and measure the energy that the Earth is receiving, knowing how far away the sun is, we can actually calculate how much energy the sun is physically producing, or its luminosity. And when we measure the luminosity of the sun, we get a number that is enormously large. The luminosity of the sun is 3.9 times 10 to the 26 watts. And I'm going to use the unit of the watt because that's what most people are familiar with. This is the same unit that you would talk about if you're referring to the energy of a light bulb, a 100-watt light bulb, a 60-watt light bulb. So 3.9 times 10 to the 26 watts. Most people are not familiar with scientific notation, and when we show them a number like this, there's not much you can make of that. It's just almost like a foreign language. So what I'm going to show you is the long version of this. And what I want you to notice is 3.9 times 10 to the 26 watts is this very, very large number. So what you are looking at is the amount of energy that the sun produces every single second. So in 1 second, the sun produces this much energy, and it does it every second of every minute, of every hour, of every day, of every year of its existence. Now, this number is huge. There's not a name for a number that big, and it shows you that stars are capable of producing an enormous amount of energy. But I want to put this into context by giving you some numbers to think about and compare with. What I have done is I looked up the amount of energy that we use on Earth if we took all the energy that every person uses in an entire year and we multiply that by every person on Earth. In other words, the amount of energy that we need to satisfy our energy needs on Earth in 1 year is 1.5 times 10 to the 13 watts. This is a number you can find on the internet. Now, if we could harness the sun's energy for just 1 single second, that 1 second's worth of energy would satisfy our needs for energy here on Earth for 26 trillion years. So what that shows you is that in 1 single second, the sun produces an incredible amount of energy. And if we have the ability to harness that energy, collect it through solar cells, solar energy collectors, then we could definitely satisfy our energy needs. So solar energy is an enormous amount of free energy, and it's simply because the sun produces so much energy. You'll notice on the screen that I've introduced a strange-looking unit, this capital L with this weird circle and a dot in the middle of it. This symbol that you see right here is the astronomical symbol for the sun. Anytime you see this symbol, you should interpret it as of the sun. So L means luminosity, and together this means luminosity of the sun. And the reason why we do that is because it's convenient to use a symbol to represent a number. That way we don't have to write the number over and over again, and we can also use it as a comparative thing. Let me show you an example. There are stars in our universe that are very, very luminous. They produce an enormous amount of energy. These stars produce 10 to the 6 solar luminosities. Now what that means is one single star produces the equivalent of 1 million times the energy of the sun. You could say 1 million times this very big number here, which is also a big number. Or if you just do it like this, you can say, okay, this star is producing the equivalent amount of energy as our sun if we had 1 million suns all together producing energy. So one star is 1 million times the energy that the sun is producing. These are very luminous stars. The flip side of this is the least luminous stars in our universe produce very little energy. The least luminous stars in our universe will produce something like 1/10,000th the amount of energy that the sun does. This means that you would have to have 10,000 of these stars to equal what the sun is producing every single second. So you can see that our sun is not the most energetic star in the universe. It's not the least energetic star in our universe. There are some stars that produce way more energy than the sun does, and there are stars that produce way less energy. And it is simply something you can't see by looking at the star. You have to measure other things about the star to know how much energy it's producing. And it always helps to know how far away the star is. So it's very critical that you understand that the concept of luminosity and brightness, although they sound very similar, they are very different but related ideas. And it's important that we separate them out. You see the brightness of something, you measure the amount of energy that it's producing. The amount of energy it produces never changes, but the brightness changes as you change your distance. And what we'll see in a future video is how we can take both of these ideas and allow them to work to show us various properties of the stars. We're just about out of time, so I hope you'll join me in the next section.